All right. Welcome to New England Dynamics and Number Theory seminar. Today we're joined from Columbus, Ohio, and the title is the Hausdorff dimension of psi-well approximable numbers and self-similar sets. And the speaker is Suxuan Chen from Ohio State University. Welcome, Suxuan.
Okay, thank you for introduction, and thank you all for attending my talk. My title is the Hausdorff dimension of psi-well approximable numbers and self-similar sets. And please feel free to interrupt if you have any questions. Okay, we start with, okay, maybe I should move it somewhere. Okay, let's start with the definition. Okay, we first define psi-well approximable numbers and very well approximable numbers. Let psi be a function from n to r plus, and then we define the set of psi-well approximable numbers to be w psi, which consists of real numbers x in R such that qx minus p is less than psi q for infinitely many pairs pq and with p in z, q in n. And furthermore, we define a special class of psi, which is psi v, and it is defined by psi vq equal to 1 over q to the v. And then we define the set of very well approximable numbers to be the union of all w psi v, and we use the notation VWA to denote the set of very well approximable numbers. And there are classical results in Diophantine approximation telling us the size of w psi. The first one is Khinchin's theorem. The statement is let psi still be a monotonic function, then the Lebesgue measure of w psi intersect with the unit interval is 0 if the infinite sum psi q converges, and is equal to 1 if the infinite sum diverges. And furthermore, we have Jarnik-Basikovich theorem. This theorem was proved by Jarnik and Basikovich independently. And let psi be a function from n to r plus, and we also assume that it is a non-increasing, and let s be a number between 0 and 1, then the s-dimensional Hausdorff measure of w psi is equal to 0 if the infinite sum q to the power 1 minus s psi sq converges and is equal to infinity otherwise. And so if we look at, we can view Jarnik-Basikovich theorem as a refinement of Khinchin's theorem, because if we consider the special function psi v, which maps q to 1 over q to the v, and then for v greater than 1, then sigma psi q converges. So its Lebesgue measure is 0. But if we apply Jarnik-Basikovich theorem, we can get that the Hausdorff dimension of w psi v is 2 over 1 plus v, because this value is the threshold for this infinite sum to diverge. And if we look at this expression as v goes to 1, the dimension 2 over 1 plus v goes to 1. Therefore, since the very well approximable numbers is the union of all w psi v for v greater than 1, we have that the Hausdorff dimension of very well approximable numbers is 1. Okay, and one can further investigate the distribution of w psi in the real line or unit interval by consider the intersection of w psi with some sets that has been well studied. So we have Mailer's question. It was raised by Mailer in 1984. The statement is how close can irrational numbers of Cantor set be approximated by rational numbers not in Cantor set. And here we can interpret Mailer's question as the size of W psi with Cantor set. And more generally, we can consider the intersection of W psi with self-similar sets, because Cantor set can be viewed as a special case of self-similar sets. Okay, to illustrate self-similar sets, we give a brief introduction to iterated function systems. Okay, an iterated function system is a finite collection of functions fi mapping from R to R of the form fi is equal to aix plus bi. Here, ai is a real number, is some real number between 0 and 1, and bi could be taken to be any real number. And there are some facts from fractal geometry. Suppose we are given an iterative function system, then there is a unique compact set V invariant under the iterative function system in the sense that V is equal to the union of the image of V under those Fi's. And if we assume the open set condition, which is a technical condition in fractal geometry, then we can compute the Hausdorff dimension of this self-similar set. Compute the Hausdorff dimension of this compact set. It is equal to S, and S is the unique number such that if we raise those AI to the power S and sum over those I's, we get 1. And recall that these AI are the coefficients of X. And we also call these AI contraction ratios of the iterated function system. And furthermore, if we assume open set condition, then there exists a unique measure mu supported on V, satisfying that mu is equal to the push forward mu under those Fi and weighted by AI to the power S. And we say that mu is invariant under this iterative function system. And moreover, there are some good property of this mu. If we consider a one-dimensional ball centered at X with radius R, then the mu measure of this ball is about R to the power S. So this one-dimensional ball is really an interval X minus R, X plus R. And we need to assume that this X to be a point inside V. And such sets V and measures mu are called self-similar sets and self-similar measures. And there is a classical example of iterative function system. We can consider f1x to be equal to 1/3 x and f2x to be equal to 1/3 x plus 2/3. Then the self-similar sets associated to the iterative function system f1, f2 is the middle third Cantor set. Okay, does anyone have any question about the introduction part up to now? Okay, then we can keep going. Okay, now let's look at some progress in this direction, which means the direction of considering the size of W psi intersect with self-similar sets. Okay, so first, Kleinbach, Lindenstrass, and Weiss proved that the mu measure of very well approximable numbers is equal to 1, where mu is a friendly measure. And here, friendly measure contains self-similar measures. And then Khalil Luthi showed that Khinchin type result holds for self-similar measures under the assumption that the underlying iterated function system is rational and satisfies the open set condition, and that the support of the self-similar measure has large Hausdorff dimension. So if we go back to Khinchin's type theorem, this means that if we replace this Lebesgue measure by mu, where self-similar measures, then this result still holds. And then later, Data and Yana proved that Khinchin type result holds for broad probability measure on R. And if assuming that the broad probability measure has certain Fourier asymptotics, and it includes a subset of self-similar measures. And by very recent work of Bernard, He and Zhang, Khinchin type result holds for all self-similar measures. So now we have no assumption on this mu. It holds for this result holds for all self-similar measures mu. Okay. And what we have mentioned are all about Khinchin type result. So one can further consider Jarnik-Basikovich type result, which is about the Hausdorff dimension of psi-well approximable numbers or very well approximable numbers. Okay, there are some conjectures on the intersection of very well approximable numbers and Cantor set. So we let K denote the middle third Cantor set. There is a conjecture by Lebesley, Sub, and Villani in 2007, saying that the Hausdorff dimension of Cantor set intersect with very well approximable numbers is equal to the Hausdorff dimension of Cantor set. So this says that very well approximable numbers has full Hausdorff dimension within the Cantor set. And another conjecture by Bujold and Durand in 2016, stating that the Hausdorff dimension of K intersect with psi-v well approximable numbers is equal to the maximum value among the Hausdorff dimension of Cantor set divided by v plus 1 and 2 over v plus 1 plus the Hausdorff dimension of Cantor set minus 1. And indeed, the second conjecture implies the first conjecture, because for v very close to 1, by this conjecture, the Hausdorff dimension of K intersect with W psi v should take the second value. And as v goes to 1, the second value goes to the Hausdorff dimension of K. So the first conjecture is an implication of the second one. And naturally, we could ask if the conjectures still hold when the Cantor set is replaced by a self-similar set. Okay, there are some known results for missing digit sets. By the work of Han Yu, the Hausdorff dimension of very well approximable numbers intersect with a missing digit set is equal to the Hausdorff dimension of this missing digit set, under the assumption that the missing digit set K has large Hausdorff dimension, which means the Hausdorff dimension should be very close to 1. And also, he has some progress on the second conjecture. The Hausdorff dimension of K intersect with W psi v is equal to the conjectured value if V is sufficiently close to 1. And also K has large Hausdorff dimension. And this work was further improved by Cho or Zhu and Yu. They improved in their joint work, they improved the dimension restriction on A. So now K can be taken to be the missing digit set of base 7 with 1 digit missing. And for this result hold, which is the first conjecture by Leversley, Sup, and Villani. And so we want to prove a result that has no restriction on the Hausdorff dimension of the set K for both of the two conjectures. Okay. Now we state our main theorem. Okay. Let F be an iterated function system satisfying the open set condition, and let K be the self-similar set associated to the iterated function system F, and let S be equal to the Hausdorff dimension of K. And we assume, suppose psi is a monotonically non-increasing function and it's not decreasing too fast, then we have a upper bound for the Hausdorff dimension of W psi intersect with the self-similar set K. It's the infimum of L such that the summation Q to the power S minus L times psi to the power 1 plus L minus SQ converges. And specifically, if we take this psi to be psi v, then we can compute this value. We can compute this infimum. This infimum is S minus 1 plus 2 over V plus 1, which matches the conjectured value of Bujold and Durand. And also for V greater than 1 and close to 1, we can find a lower bound for the Hausdorff dimension of W psi V intersect with K. There exists a constant C such that the lower bound is such that the Hausdorff dimension is bounded below by S minus C times 1 minus 2 over V plus 1. So we have the two differ by a constant C. And in particular, if we take V to be, we take the limit V goes to 1, then both the upper bound and lower bound goes to the Hausdorff dimension of K, which is S. And recall that very well approximable numbers is the union of all W psi V for V greater than 1. So we have that the Hausdorff dimension of very well approximable numbers intersect with K is equal to S, which is the Hausdorff dimension of the self-similar set K. Okay, let me pause for a second and see if people have any question with the statement. Oh, sorry, I cannot hear you.
Oh, sorry. So what does closeness to 1 mean? Is it something explicit?
Yeah, this close to 1 is related. Later, we will state that the effective equal distribution theorem from Bernard He Zhang, and this is let's say this how close of V, the distance from V to 1 is determined by the rate of effective equal distribution.
But is it the same for all fractals, or it depends on K?
It depends on, because Okay, let's see.
So you start with K, and then you have this epsilon,
Yeah.
which is epsilon neighborhood of 1, and also C.
Yeah.
So these parameters depend on K, right?
This C depends on K, but this V, this C depends on K, but the distance from V to 1 doesn't depend on K. Depends
Okay.
on the rate of effective equal distribution.
Mm-hmm.
Yeah.
Okay, so according to Asama's comment in chat, rate should depend on K also. This seems reasonable.
Okay.
Maybe you have some kind of very thin compact set, very thin fractal.
Oh.
Anyway, it was just a question. Go on. Thanks, Asama.
Oh, okay. Yeah, thank you for helping me answering the question. Okay, the proof of our theorem relies on the effective equal distribution of self-similar measures. So here we state the effective, state this result by Bernard, He, and Zhang in 2024. Let G be equal to SL2R, gamma be equal to SL2Z, and GT be the one parameter diagonal matrices with ET, e to the negative t in the diagonal entries, and UT be the one parameter unipotent group with X in the upper right corner. And let mu be a self-similar measure, and then there exists a constant C such that for all t greater than 0 and for all phi in CC infinity G mod gamma. So this means the smooth function on the homogeneous space G mod gamma with compact support, then the, oh, okay. Okay, yeah, so I'll try this. See. Okay, maybe this is better now.
It's fine with me.
Okay. Okay. So we just finished with the condition. Then we have the following effective equal distribution result. If we integrate the function phi with the variable gt ux gamma over the self-similar measure mu x, then it is equal to integral of phi over the homogeneous space G mod gamma and plus some arrow term. This arrow term depends on phi and the starting point x.
And again, continuing the previous discussion, the C depends on mu, naturally.
Yeah.
Okay. So this epsilon distance from V to 1 will depend on C.
Yeah. And
okay.
Sorry, there is a typo here. And maybe I should write, let's say, H gamma. And this is the injectivity radius at H. Because otherwise it doesn't make sense. And so for the left-hand side, we put the measure in the upper right corner of ux, and on the right-hand side, it's the integral phi on the homogeneous space against the Haar measure on the homogeneous space G mod gamma. Okay, yeah, and this C depends on the self-similar measure mu. And a few remarks. The case when the homogeneous space is SLNR mod SLNZ is also resolved by very recent work of BHZ. They posted their new archive maybe 1 or 2 months ago, and a similar result has been previously obtained by Cleo and Luthi, where the effective equal distribution with the parameters of the IFS restricted to rational numbers and the associated self-similar set having large Hausdorff dimension, and their work works for all dimensions as well. Okay, and now let's go to the proof part. Okay, to do the proof, first we introduce some sets, and we will use these sets to approximate psi-well approximable numbers. Okay, first we let AM psi to be the collection of X such that there exists PQ, which are primitive vectors. This means that PQ are co-prime, such that Q is between 2 to the m and 2 to the m plus 1, and Qx minus p is less than psi 2 to the m. So we can view AM as the collection of many intervals, because from here we can see that if we divide both sides by Q, we have X minus P over Q less than psi 2 to the m over Q. So so this gives us an interval of P over Q. And if M is very large, the intervals in A M psi are disjoint. So A M psi is indeed the union of many intervals centered at a rational number PQ with denominator between 2 to the m and 2 to the m plus 1, and the diameter is 2 times psi 2 to the m over 2 times psi 2 to the m over Q. And this AM psi can be used to approximate W psi. And indeed, in this case, dim sub AM psi is contains W psi by a very easy argument. And then how do we use the effective equal distribution result to get the measure estimate of AM psi? So from the number theoretical set, we want X to be inside AM psi, and we can convert it to the dynamical set side. If X is in AM psi, then GTUX should be inside VM. Here, VM is a neighborhood of the cusp in the homogeneous space, SL2R mod SL2Z, and this value T is determined by the function psi and M. So maybe we can draw a picture to show this. Consider the homogeneous space G mod gamma. Oh, yeah, sorry, there should be a gamma here. Gamma is equal to SL2Z. So we have UX gamma, and VM is a cusp region. And after float by GT, we want this GT UX gamma. We want this point to be inside VM. And it's a well-established connection between number theory and homogeneous dynamics. And by using this relation, we can estimate the measure of AM psi. So for the left-hand side, we just use mu AM psi And for the right-hand side, we have GTUX gamma multiplied by the characteristic function of Vm, because if X is inside this set, then GTUX gamma is inside Vm. So we have this inequality. Okay, and then for the second one, it should be they are equal up to a constant. Now we multiply chi m, we convolve chi m with a smooth function to get a smooth function. And the variable remains the same, and we still have this expression. And now by effective equal distribution, this measure, this integral is equal to phi m. The integral phi m on the homogeneous space G mod gamma with respect to the Haar measure G mod gamma plus an arrow term. And this phi m is equal to the convolution of chi sub Vm with this smooth function theta. And we can compute this integral explicitly. It's about 2 to the m times psi 2 to the m. And we still have this arrow term. Okay. Okay, does anyone have any question up to now? Okay, so we just used the effective equal distribution result to get a measure of mu am psi. And now we are able to use this this measure estimate of am psi to give an upper bound of the Hausdorff dimension of W psi intersect with a self-similar set. Okay, we let am psi star denote the collection of intervals in am psi that have non-empty intersection with the self-similar set K, which is the support of mu. And we let am star 2 psi be the collection of intervals obtained by doubling the intervals in am star psi. So let me draw a picture to illustrate this. Okay. Okay, suppose we have the real line R, and we consider the concentration of the self-similar set K. These are support of mu, which is equal to K. And we consider am psi. Recall that they consist of intervals, this set. So they may intersect in this way. And now we double the intervals in am psi. So, okay. This set, the second interval is not has no intersection with the self-similar set, so we don't consider it. We only consider the intervals that has non-empty intersection with the self-similar set K. And then okay, once we have finished doubling the intervals in AM star psi, then each of interval contains a one-dimensional ball centered in K with radius at least psi m over 2 to the m plus 1. Okay, first we recall that the diameter of intervals in AM psi, they are about size. Is about psi 2 to the m over 2 to the m plus 1. So if we double them, and here they have an intersection already. So if we double them, they will contain a one-dimensional ball centered in K with radius at least psi 2 to the m over 2 to the m plus 1. Okay, maybe I should zoom in here a bit. Oh, sorry, I just need to charge the laptop. Oh.
Okay, any questions while the laptop is being charged?
Okay, then let me restart. Here it's a bit confusing why we need to double these intervals. So let us zoom in a little bit. Oh, while it was charged, it's hard to draw it's hard to write. Okay, we'll charge later. Let's say this is the concentration of points in the self-similar set K. And suppose we have an interval that intersect with K, and we really want an interval such that and now we want to estimate the
or are you still trying to draw something?
Yeah. So I want to kind of forget it because I try to explain why we need to consider the doubled intervals to estimate the number of intervals in AM star psi. Oh, okay. Yeah. Sorry, I finally figured this out. Because these intervals, okay. Okay, because here the intersection can be very weird. Suppose we have this concentration of K, and then suppose here we have an interval of AM psi, interval in AM star psi, which means it has non-empty intersection with the self-similar set K. We want to, in order to use the measure estimate of AM psi to get the cardinality of AM psi, we need to estimate the measure of this interval. However, this interval, we don't know how much percent of the interval is has intersection with the set K, so we double the radius. Now we view this point as the center. So for the one-dimensional ball centered at this point, it's completely contained in AM2 psi, which is the doubled interval. So for this long interval, so for this double interval, it completely contains a one-dimensional ball with center in K and the radius of psi 2 to the m over 2 to the m plus 1. Therefore, we can get a measure estimate of a lower bound for the measure of balls inside AM2 psi. Okay. Yeah, sorry for the for this blank period. And so that's the reason we want to double the radius of intervals in AM star psi to get AM star 2 psi, and it contains one-dimensional ball centered in K with the radius at least the radius of one-dimensional balls inside AM star psi.
So there was also an error estimate, right, for this measure of AM of psi?
Oh, maybe your question is the measure estimate of AM2 psi.
So there was an error of some exponential decay.
Exponential. For the measure estimate of this ball, we didn't use the effective equal distribution. We used the property that one-dimensional ball, if it is centered in the self-similar set with the radius not small, then its measure is approximately r to the power s, with s being the Hausdorff.
Yeah, I mean the second inequality.
The second inequality, yeah, it's from the effective equal distribution.
Okay, so Okay, all right. Yeah, thanks.
Oh, okay. Thank you for the question. And yeah, so we have the cardinality of AM2 psi multiplied by the measure of one-dimensional balls, which is this. It should be less than the measure of AM2 psi. And for this AM2 psi, we have effective equal distribution. It's less than 2 times m times 2 times psi 2 to the m. And so with this, we are able to estimate the cardinality of AM psi, because AM psi, AM2 psi is obtained by doubling the intervals in AM psi. So they have the same radius, and then from the above, we can get an estimate of the cardinality, which is this value. Okay. And with the obtained value, we are able to give an upper bound. Okay, one thing I forgot to mention is that suppose we are given a delta greater than 0, we can choose m delta large so that the maximal length of the intervals in AM psi is less than delta. And with this information, then the union of AM psi is a delta cover of the lim sup set of AM psi intersect with K. And since this lim sup AM psi contains W psi, the intersection contains W psi intersect with K. And we can use this to compute the L-dimensional Hausdorff pre-measure of W psi intersect with K with the parameter delta. And recall that it's defined to be this value is defined to be the summation of those diameters of the cover raised to the power L. And okay, since we have this delta cover, now we just do the calculation. We have the number of intervals inside AM psi, and that's their maximal length or maximal diameter. We raise it to the power L and sum over all the m from m delta to infinity. And with the above estimate on the cardinality of AM psi, we have the second inequality. And then furthermore, this one can be reduced to q from 2 to the m delta to infinity, q to the power s minus l times psi 1 plus l minus sq. So now we take delta to go to 0, then the right-hand side, we want to figure out if the right-hand side converges or diverges. So if we require that the summation of q to the power s minus l times psi 1 plus l minus sq diverge, then as delta goes to 0, m delta goes to infinity, so the right-hand side go to 0. And then using the definition of L-dimensional Hausdorff the L-dimensional Hausdorff measure, we take the limit, we get that the L-dimensional Hausdorff measure of W psi intersected with K is equal to 0. So that's the proof for the upper bound part. Maybe the critical part is try to double the radius to count the cardinality of AM star psi.
Sorry, I heard about while computing the measure of AM of psi, the second inequality again in the previous slide.
Oh, previous slide. Okay.
Yeah. So here it could happen that if psi is, for example, decaying too fast, then this term could be smaller than the other that we got.
Yeah. Yeah, that's a good question. Thank you. So that's why we require that psi not decreasing too fast. We want the main term to majorize the arrow term.
Oh, okay. Thanks.
Yeah. If psi is not decreasing too fast, then we get an effective estimate. Yeah, thank you for getting that question. Okay. Okay, maybe we don't have enough time, but I'll just try as much as I can to go to the upper bound part. Okay, for the upper bound, we need some symbolic dynamics to do some coding. So first we define branches of mu, and for k in n, we let I sub k to be the collection of k tuples with the entries between 1 and L. And we let I to be equal to, actually this should be I sub 0 to be the empty set, and we set I sub star to be the union of all those IKs. Okay, and now for a tuple alpha I1, I2, IK inside of the set I sub k, we define F alpha to be the composition of Fi1 up to Fi sub k. And since these Fi, recall that these Fi's are the functions inside the iterated function system, they are of the form A sub Aix plus B sub A sub I1 x plus B sub I1, for example, for this Fi1. And then, so it's also a linear function, and we can write it as C alpha x plus B alpha. And this C alpha is a product of the coefficients of those F sub ij's. And B alpha is the value of the function at 0. And we say a branch of mu is a push forward of mu by some F alpha, and with alpha inside I sub star. And we write F mu alpha in the form, the push forward of mu by F alpha. And then there's a lemma that mu alpha is a self-similar measure associated to the new iterative function system, which consists of functions of the form F alpha composed with Fi composed with F alpha inverse. So it's very close to the original iterative function system, but we compose and pre-compose with F alpha and F alpha inverse. And then the unique compact set invariant under F alpha is the image of K under F alpha, and it is also the support of mu alpha. And this unique compact set also has Hausdorff dimension S, which is the same as the Hausdorff dimension of the original self-similar set. And now once we have the result that mu alpha is also a self-similar measure, we can consider the effective equal distribution of mu sub alpha. And for this, we need to use the previous effective equal distribution result of mu. And so we integrate the same thing against the new measure mu sub alpha. We can rewrite mu sub alpha as the push forward of mu by F alpha. And then by change of variable, we move the F alpha inside. So now the new variable is F alpha x. And recall that this F alpha is a linear function, so we can rewrite it and then do some argument. And then we can reduce this integral into the integral of phi against the Haar measure G mod gamma plus some arrow term. Yeah, sorry, another typo here. This C sub theta should be C sub alpha. where the alpha is where C alpha is a product of C sub ij from I to j, and it's the coefficient of f sub alpha. So for this new measure.
Wait, sorry, can you say it again? You actually have a formula for C sub alpha?
Oh yeah. This C alpha is a product of the coefficients of Fij's.
And what are Cij's?
Oh, Cij, they are the coefficients of Fij.
Oh, no, the contraction rates? No, not the contraction rates.
Yeah, they are the contraction ratios.
Oh, C alpha. Oh, okay,
Yeah.
I see. All right, I got it.
Okay. Yeah, so now this
But can I okay. Yeah, all right, fine. Thank you.
Oh, okay. Thank you. So for this mu alpha measure, the push forward of mu by f alpha, for the arrow term we have an extra C alpha to the -1 minus C over 2, and by this effective equal distribution of mu alpha, we can estimate the mu alpha measure of AM psi, which we use the same correspondence before. Yeah, sorry, another typo here, because I used a previous slide and forget to change some things. And mu alpha of AM psi is bounded below by C times 2 to the m psi 2 to the m minus the arrow term C prime times 2 to the m psi 2 to the m squared, and minus C alpha to the power -1 minus C over 2 times a constant depending on the iterated function system f and the same arrow term as before. Okay. And then now we define the one-sided shift space omega L. It consists of the infinite one-sided sequence omega, which are, if we write the entries omega 1, omega 2, omega I, etc., and those entries are integers between 1 and L. And for an element omega in the space omega L, we let omega sub k be the k tuple obtained by truncating omega right after its kth entry. And then there's a result by Hutchinson that stating that for every omega in omega L, the intersection of k from 1 to L f sub omega k, the image of k under f sub omega k is a point in k, and the map defined by the map from omega L to k defined by pi omega, which is the intersection of k from 1 to infinity f sub omega k of k, is surjective. So as an example, we can consider the middle third Cantor set. Okay. Okay, let's say we have the functions f1, f2 as before, and we have let's say we have an infinite sequence 1, 2, 1, 2, 2, and etc. Let's see how how this omega is mapped to a point in the Cantor set. So we have the unit interval, and then under F1, then we have F1k here. So now this point should be inside this one. And then we have 2 here, so we use F2. And then we have 1 again, so we have the first one, and then second one again, and then second one again. So if we consider the intersection of all these images, we finally get a point. So that's how this omega L is mapped to the self-similar set K. And moreover, for the K tuple alpha, then the support of mu alpha, which by a previous result, it is equal to F alpha of K. It consists of the elements in omega L, such that if we truncate it after the kth entry, then then we get I1, I2 up to I sub K. So basically, it's saying that the support of mu alpha consists of the elements in omega L such that its first K entries are of this form. So as an example, so support of mu alpha omega 5 should be contained in this interval. And with this setup, now we are able to find a lower bound for the Hausdorff dimension of W psi V intersect with K. So the strategy is to construct a limit set sitting inside W psi V intersect with the support of mu, which is the self-similar set. And then we give a lower bound for the Hausdorff dimension of this limit set. So in the following, I give a sketch of the construction. First, we choose M1 to be a large number such that the estimate of A sub M1 psi V is effective, which means the main term majorizes the arrow term. And we collect those intervals that have non-empty intersection with K and denote this set by A sub M1 star. So here I draw the real line, and the blue curvy lines, they denote the support of mu, which are the concentration of points inside of the self-similar set. And the red intervals, they are intervals in the set A sub M1 psi V. So recall we defined this before. They are intervals, and we take those intervals in A sub M1 psi V that has a non-empty intersection with support of mu. So the first one, second one, the first one, the third one, and the sixth one. So we take them and denote this set by A sub M1 star. And by an argument similar to the previous one, we have an estimate on the number of intervals inside AM star, and we can compute it explicitly by the same technique as before. Is this value due to the M1 V plus 1s minus M1 times V minus 1. And then in step 2, for each interval inside A sub M1 star, we choose a branch mu alpha inside this interval such that the diameter of supported mu alpha is comparable to the length of the interval. Yeah, let me briefly explain why we can do this. Because previously we have that, let's say if X is inside K, then we have the map from omega to K, from the shift space to K. And we have a pre-image of X inside omega L, which let's say we have I1, I2 up to ij, etc. And then we want to choose a branch of mu, so that a branch mu alpha of mu such that x is inside support of mu alpha. And then we just truncate, let's say truncate it at some point such that those c sub I1 up to c sub IN is the okay. Maybe we should go back here. Okay. Because we have the support of mu alpha is equal to f alpha times the support of mu. So the contraction ratio of f alpha is c sub alpha, which is c sub I1 times c sub I2 up to c sub IN. We want this value times the diameter of support of mu to be comparable to the length of intervals in AM1 star. So it is doable because we can truncate this x at some point to get this support, to get this mu alpha.
Okay, maybe you can try to wrap it up a little bit because people will probably have to leave it too.
Oh, okay. Yeah, I'll finish quickly. So we can zoom in this part a bit. This is an interval in AM1 star, and the red line is AM1 star, and the blue curly line is the concentration of the compass at K. So we zoom in it a bit, then we will see some pattern like this. And these new red lines are intervals in AM sub 2 psi v. We consider the intersection. So now we take this new concentration part. It should be the support of some branch of mu. And we zoom in a little bit, we see the same pattern. So so we choose these good intervals in A sub m2 psi v and collect them to get the new collection of intervals A sub m2 star psi. Sorry, A sub m2 star. So and then in step 3 we repeat this process, and then we can obtain a sequence of A sub mn star. If we consider the union of the intervals inside A sub mn star, then it's a decreasing sequence. And we have estimate of number of intervals in A sub mn star inside a single interval of A mn star, which is this value. And moreover, this limit set is contained in the intersection of psi-well approximable numbers intersect with K. So that's a picture to illustrate this. And now we can define a measure on the limit set. Because so first we distribute the measure 1 evenly to each of intervals in the first level, and then in the second level we distribute the measure of the first interval evenly into the sub-intervals contained in the first one. So we keep doing this process for each of these interval and repeat it. Then we can get a measure on the limit set. And we have a mass distribution principle. It says that if we have a set F and there's a measure on the set F, and suppose we have a set U, and the measure of U is less than C times the diameter of U raised to the power L, then we have a lower bound on the Hausdorff dimension of F. So that's how we find the lower bound of the Hausdorff dimension of W psi v intersect with mu. By the previous process, we can get a measure on the limit set, and then we also have an estimate on the measure of each intervals at the nth level or n+1th level. So here we do an interval in the n+1th level. We have a measure estimate, and then we let U be an interval such that U intersect with a self-similar set to be non-empty, and we suppose the diameter of U is comparable to the length of intervals in A sub mn star. Then now we use the intervals in A sub. Okay, I'm very sorry for the typo. A sub m n+1. Use the intervals in the next level to cover the set U. So its measure is bounded by the summation of intervals in the n+1th level that has non-empty intersection with U, and we can show that it's bounded by diameter of U to the power T. Using the information that we know that the number of intervals contained in a single interval in the previous level, and using this we can have a measure estimate of the set U, and use this we can obtain a lower bound. Okay, I'll stop here, and sorry for the.
Okay, thank you. Let's give Suxuan a round of applause. Nice talk. Maybe some quick questions.
Okay.
Any questions, comments? So I'm curious certainly about the second paper of Bernard and Zhang and the higher dimensional version of Khinchin's theorem. Does it? Can you use this? Their new result to get a high dimensional analog?
Oh, yeah. Thank you for that question. So here, because we are using the intervals in. Oh.
Yes.
Okay. Because we consider A per psi and use this to. Okay. Yeah.
Yeah. You need intervals, but what's the answer? It's harder.
It's harder because A per psi in one-dimensional case, if the psi q converges, then the intervals in A per psi they are disjoint. But for higher dimensional case, they are no longer disjoint.
Okay, so it's more difficult.
Yeah.
Okay, understand. Any other questions? Okay, well, let's thank the speaker again. It was a really nice talk. I hope we'll hear from you on some generalizations. And until next time.